All right. Can someone, because I don't want to do it like the last review session, can someone just confirm that they can hear me?
I can hear you.
Yes, okay, excellent. All right. Okay, so it's not like a repeat. Excellent. Very good. Okay, so hello everyone. Um, as you know, this is your Comp 335 final exam review session, well, hosted by me. I know you had another one before this. So for those of you that just got here, there's a link at the very top for the slides that I'll be using. For those of you who aren't in Dr. Shiri's section, it's the easiest way of just giving everyone the slides. So that's that. So then maybe just let me give you a quick summary of what I think we'll be doing. So the first thing we're going to do is we're going to look at some exercises from before the midterm. So just a few. And then we'll be, I'll do some Q&As just on that. And then maybe a break, I don't know, depending on how long this takes. And then some more exercises for after the midterm. So there are, I think there are 10. There are a few more for after the midterm rather than before, because that makes sense. And then some more Q&As, and then we'll wrap up. And so yes, this is being recorded, right? I didn't forget to record. Yes, okay, it's recording. Yes, so there's the recording button that's going on. So so we're all good. So it's being recorded, and everything's going to be okay. All right. So if there are no preliminary questions, let's get started. So hopefully some of you in Dr. Shiri's section had maybe some time to look at these questions. If not, that's fine. So and also what I usually do in my tutorials is I give people like maybe a couple of minutes to try the question out, and then we go over them together. So that's what I plan on doing for this as well, because that's the best way for you to sort of make sure you're ready and things like that. Okay, so this first question, essentially the idea that I was trying to come across here is I want you to make sure that you know your language definitions, how to manipulate different language operations. And so we're given the following. In this case, it's just an alphabet, and we want to know how many strings we have in sigma plus, different sigma cube, sigma star. So maybe take a minute to try this one, and we'll look at it together. And so for the person who asked which PDF it is, it's the one that's called Final Review. So I think it's the one at the very top. Like it should be at the top of the collection of slides. Okay, so yeah, so take a minute, and then we'll look at it together. All right, so I think that was some time to get you started. for the person, and I'm sure a lot of people wondering how long this is going to take. So it'll take as long as it needs to take, but I don't think it'll take longer than maybe 2 hours, depending on the number of questions and things like that. It could take a lot less. It depends on participation. All right, so let's look at this question. So maybe just as a reminder, but hopefully everyone knows this by now. What is sigma plus, or in other words, what is just a language? Because if you think about it, this is just a set of strings, and a set of strings is by definition a language. So what is the definition of sigma plus, or actually just really L plus? So it's just the union where you start with sigma to the 1, which is just sigma itself, union sigma square. So this is just sigma and then the language concatenation with sigma. So just as a reminder, that would just be you take ABC and then you take ABC again, and you concatenate every string in this language with every string in this language, basically. And then you keep going, so you do it for the third power and so on until infinity, right? So that's the definition for sigma plus. What's the only difference between sigma plus and sigma star? Sigma star, as you already know, it's just you start the summation at 0, right? So you do sigma 0, union sigma 1, union sigma 2, and so on. Okay, so that's just a reminder of the definition. So what is that? What is the actual question asking for? Well, it's asking for sigma plus difference, sigma cube, sigma star. Okay, so whenever you have questions like these, I find that the easiest thing is to try to expand the few terms for your formula and see what's actually going on. So for sigma plus, just apply the definition, and you get this. So remember, we're trying to find the number of strings, right? We don't really need to list them. And then we're going to take sigma cube and then apply for concatenated with sigma star. So that would be something like this, right? Okay, so how is this useful? Well, there's kind of this property that you have for languages that if you have, let's say, L1 and then L2 union L3, then this is equal to L1, L2 union L1, L3. Okay, and sort of an intuition behind that is because let's say you have L1 is just X, and L2 is Y, and L3 is Z, so you have this. Then the operation of concatenation is you're taking every element from L1 and concatenating it with every element from here. So you take XY and XZ. But that's essentially the same thing as doing X concatenate Y, union X concatenate Z. So that's the intuition behind it, okay? So why am I talking about this? Well, now you just have to kind of deal with this, but with exponents. So this third power, it's you take this third power and you kind of concatenate it with this 0th power. Yeah, so is there a problem with that might be an issue I might have to address?
Yeah.
Yeah.
There was just like some scratching going on with somebody's mic. I don't know if it was yours or somebody else's.
I'm not sure. If I don't speak, maybe I think
it was like if you were moving the mic around or something.
Oh. Okay.
Yeah.
I don't know. It happens when you write. Well, that's bad because I need to write.
Right.
Okay. Let's keep on going and let's see how I don't know. I could switch to my I have another drawing tablet. So if that's bad, then we could do that. But okay, so I'll try not to move my mic then. But okay, so what was I saying? So you want to take this language here, basically because, you know, sigma cube is just, you're concatenating sigma with itself 3 times, and that gives you a set of strings, and a set of strings is a language. So you're just gonna apply that essentially, that concatenation and this rule to each of these languages here. So basically what that's going to give you is, I'm just going to rewrite this here. So you're just going to get, well, what's sigma 0? So sigma 0 is just the set containing lambda. And the set containing lambda is just, you know, if you take any language and you concatenate it with the set containing lambda, then hopefully everyone sees that this just gives you that language, because every string in here is being concatenated with lambda, but we know that x lambda is equal to x. Okay. So what happens then for the first term is you just get sigma q, and then for the next term you're just going to get every string of length 3 is going to be concatenated with every string of length 1, sorry. So logically, just intuitively, that's going to give you every string of length 4, right? So that's why here I'm going to write this is minus sigma 4. And then hopefully you see that the next term is sigma 5, and you just keep on going. Okay? So I have these terms here, and notice another useful property is each of these are disjoint, essentially. So that means there's no overlap. So if you have this expression and you're doing difference this expression, then there is no kind of, you don't lose any generality by saying that all of the elements here get sort of canceled, quote unquote, with all the elements here, and then all the elements in sigma 4 here get canceled with these guys. So and then you sort of keep on going. So you see that everything gets eliminated except for these 2 guys, right? So what the result is you just get sigma 1 union sigma square, right? And by sigma square I mean the language concatenated with itself. So then what was the actual question? The actual questions we were interested in is how many strings are there in here? So now if you just want to take the cardinality of this, cardinality, or the number of elements in this language, then because I know that these 2 guys are mutually disjoint because there's no overlap, then I can just say that this is just sigma, the cardinality of sigma plus the cardinality of sigma square. And then this is some easy math. So the cardinality of sigma is 3 because there's 3 elements, and then the cardinality of sigma square is 3 square. So you get 3 plus 9, which is 12. Okay, so that's how you would tackle this kind of question. And just in general, the main idea I was trying to come across in this question was try to make sure you know all your definitions, and try to make sure you know how to manipulate sets, like in this kind of exercise. Okay, any questions about this? I feel like this is pretty straightforward, and it seems like there's no more squeaking, which is nice. It is good.
It's a bit better.
It's a bit better. All right. Okay, so it's not entirely better, but I'll take it. Okay. So that was, yeah. So the solution is there. It's 12. All right. So now switching gears to FAs, right? So we looked at languages first in the course, and then we shifted to DFAs and NFAs. So just a reminder, in general, what is an FA? An FA is, just think of it as a machine where you take a string W over some alphabet sigma. You feed it into this machine, into this FA, and then it answers either one of 2 things. So it either answers yes or no, right? And depending on what it answers, and depending on what every string you give it answers, then this FAM, let's just call it M, is going to define accept a given language. Okay, so L of M is the language accepted by M, right? It's the set. Well, yeah, you can just, that's kind of poor notation, but I think everyone sees what I'm saying. So there isn't a question about constructing FAs because you can't do that in an MCQ, but there is an MCQ which has to do with FAs and DFAs and NFAs in general. So before we look at this question, the idea and what I wanted to make sure everyone was kind of comfortable with is make sure you understand and this isn't just for FAs, for PDAs and for Turing machines, the definition that you're given, the sort of strictly mathematical definition where FAs is a 5-tuple. So in this case, a set of states, the alphabet, the transition function, the initial state, and the set of final states. Make sure you know what those definitions are, because they can be used in questions like these. And it's good to understand the sort of theoretical basis of each machine that we've seen throughout the course. And yeah, so I'll talk a bit more about it after we solve the question. Okay, so again, maybe take a minute, try to look at it, and we'll go over it together. And I'll try to fix my mic, actually. All right, so I don't know if the sound is better, but hopefully you had some time to look at the question and to rack your brains around it. So let's look at the solution. So what is the question saying? So you're given, in this case, you're given a DFA, and you're given the standard 5-tuple definition, and you want to know which of the following statements are true. So none of them could be true. Some of them could be true. All of them could be true. So it's one of those very, very annoying multiple choice questions that I know everyone likes. No, I know no one likes these, but it's good practice. Okay, so let's go through each option. So the first one is if the set of final states F is empty, then the language accepted by M must be empty. So in other words, M cannot accept any strings. So what does someone think about this? Or what's the intuition? Well, the intuition is, you have an FA, right? In this case, you have a DFA, and you start at this initial state, right? Okay, and wherever you go, you're never going to hit a final state, right? So, what's the definition of accepting a string in a DFA? Is there has to be a path, there has to be a walk, such that you finish the string W and you end up in a final state, right? You must end up in a final state, otherwise, you can't accept that string. So yes, as a lot of you, okay, nice, good. As a lot of you are stating, this is in fact true. So yes, because just intuitively, if there isn't any place to accept, then there isn't going to be any strings to accept. What about, so is the converse true? So if the language accepted by the DFA is empty, then does that imply that the set of final states is empty? Okay, so someone said false. Okay, people are saying false.
Yeah.
Okay, all right. Okay, so everyone knows this trick. All right, yes, very good. So yeah, you could do something like this. So this is, this is a valid DFA. And then you could add essentially an unreachable state where you're never going to start here, but this is the final state. And you can have these two transitions here. And this is still a valid DFA, right? So this is why I think it's important to know the definition, because it helps you realize what a valid and invalid DFA is. If you look at the definition, you have some states, so that's fine. You have an alphabet. The transition function is well defined. So this guy, whoopsies, this guy is your initial state, and you have a final state. It's completely valid DFA. It doesn't do anything, right? It doesn't. This thing doesn't help you in anything, but what it does do is it allows you to claim that this is in fact false. So what's important to note here basically is that this statement here is not an if and only if. It just goes from the left-hand side to the right-hand side. Yes, very good, Ronaldo. Yes. There are plenty of stupid things you could do. Yes. So to put it very coarsely, this is a useless and dumb thing to do, but it's perfectly valid. So an excellent point. I also heard someone, I think someone had a question, or no? No, okay. Because I thought someone was going to cut me off. Okay. All right. So the next question is very similar. C, if instead the okay, so this I hope everyone sees that this doesn't make any sense, because if f equals sigma star is complete nonsense. So what I meant to say here was if L of m is equal to sigma star, then f is equal to q. Okay, so it's kind of the same thing as B, except that instead of the empty set, this is sigma star. So you should kind of see that if you just take this DFA and you just do the complement, you can get the same kind of, yeah, very good. So you can get exactly the same kind of contradiction, right? You can, if you just say that this is, this is going to accept all of the possible strings over AB. And then if you just add a useless, a non-final state, this remains a valid DFA. This remains a valid DFA. And so this is why the fact that F is equal to Q is false. So that's why this guy is false. But of course, if F is equal to Q, right? So if all of your states are final states, then of course, wherever you end up in your DFA, you're going to accept, right? So that means that anything you give it, any string over your alphabet that you give it, it's going to be accepted. So that's why the language accepted by M is sigma star. So this would be true, okay? And actually an interesting question for D, which I thought of after, is does this still hold if M is an NFA? So if all of your yes, Joey, all states, even including Q0, because Q by definition is the set of all states. Q0 is a state, so it must belong to Q. Yes. So if instead of asking this for a DFA, I asked this for an NFA, D does not hold if M is an NFA. Yes, very good. And so the reason for that is because in an NFA, there isn't a restriction on the number of transitions you need, right? So let's say I do this, right? This is a valid NFA, but all of the states are final states. But I hope everyone sees that the language accepted by this NFA is not sigma star. What does this accept? It accepts lambda, A, and AB, right? So that's definitely not sigma star because it's not infinite. Okay, so yeah, so what I wanted to say about this question after finishing the question is make sure you get these kind of edge cases. Make sure that when you're going over your notes, when you're going over your notes, you're looking at these kinds of edge cases, these kinds of cases where, you know, it's something silly that you would never use in an actual, like, well, in an assignment or whatever. But if you were asked this in a kind of question in a test, then it might be something that could come up, right? Because, you know, it tests if you really actually do understand what a DFA and what an NFA is, what are the definitions, okay? So there was a question about re-explaining C, which is fair because it was initially not well sort of written. So the question was, if the language accepted by M is sigma star, then this must imply that F is equal to Q. Yes, so let me just, so this is, so it's, yeah, so there's, okay. So forget this, there's a, yeah, I must have messed up, but it's true, false, false, true, okay? So for C, yeah, so there's a mistake in the slides, sorry about that. So for C, it's asking that if the language accepted by M is sigma star, so imagine just sigma is AB, right? Then it must mean, so it must imply that the set of all states Q of your machine is the same as the set of final states. So in other words, all your machine is just a bunch of final states, basically. That's what it's saying, okay? And that is not correct because I can easily create a machine like this one. So this one already, it's going to accept sigma star, right? This is a DFA that accepts sigma star because anything you give it, it's going to end up in a final state. But now if you attach it a unreachable state like this one here, then it is no longer true that the set of final states is equal to the set of states, right? So this is no longer true, but this remains true. Okay, so that's why the statement is false. Okay, so I hope that's clear. And yeah, so apologies for the, yeah, so it should say, yeah, so I'm going to fix this. It should say true, false, false, true. Okay, so I hope that's clear. Are there any other questions about this? Sorry, could you go over again? Yes, yes, for sure. For D, if M is an NFA, right? And F is equal, yeah, F is equal to Q. So many fake, wait, what? All right, okay. If M is an NFA and F is equal to Q, so let me just create an NFA where all of the states are final states, right? So this is an NFA because if I give it, for example, these two transitions, it's a valid NFA because you know, in this case, the definition for NFAs is almost the same as DFAs, except that your transition function delta can either have, you can have no transitions, you can have one transition, two transitions, so as many transitions as you kind of want, basically. So this NFA has all of its states being final states, right? Because all of the states here are final states. However, the language accepted by this NFA is not, so the language accepted by this NFA is not sigma star, okay? Why? Because, for instance, if you give this NFA B, okay? So if you give this NFA B, then let's say you feed B into here, your machine, right? Your machine, if it's reading B, it's gonna start at the initial state here, and it's going to read the B, but it's going to say, oh, I have no transitions for when I read a B, so I'm unable to move forward. I can't finish. I'm unable to go to the next input in my symbol, and so I can't finish this string. So there isn't a walk that goes from my initial state to a final state in an NFA, because here I can't finish reading the input, right? So remember how NFAs work. And so because, for instance, I can't accept B, then clearly the language accepted by M is not sigma star, okay? So, okay, there's a couple of questions. There's like four Ronaldos, that's cool. The M in C is a DFA. Yes, so for this question, M is always a DFA. So these questions are all for DFAs, but then this is like D prime, where let's say M is an NFA, because someone was asking about NFAs. Because for NFAs, you can also fail. Yes, by hanging. Yes, so that's what I was explaining. DFAs need to have transitions. Yes. So Joey, why is this NFA not a DFA? Because, for instance, well, because for a DFA, for each state that you start at, you have to have exactly the number of transitions in your alphabet. So if you start at this state, you have to have exactly the cardinality of sigma transitions. So if sigma is AB, then for each state that you have to have exactly two transitions A and B. Okay, you can't have less than two, and you can't have more than two. Okay, so that's why it's not a DFA. All right, any more questions about this? These are good questions. It's good that you're asking them now. No? Okay. All right. So yeah, so I'm going to fix this. Sorry about this. But that was essentially about looking at NFAs and DFAs. Okay. So again, just make sure you understand the definitions, make sure you know what the difference is between them, and make sure you know how exactly what the definition is for a string to be accepted by FAs. So both DFAs and NFAs. Okay. The next question is actually going to take a bit longer to explain. So I'm going to give you a bit more time to try it. So yeah, as I said, take maybe probably 2 or 3 minutes to try it, and we'll come back and look at it too. Okay. Marvin, these slides are on Moodle if you're with Dr. Shiri. If you're not with Dr. Shiri, then they can be found. Come on, I thought I had pasted. Give me a second. So while people are working on that, I'm going to repaste. Oh, okay. Thank you, Kevin. They can be found there. Thanks. Yes. Okay, so take 2 or 3 minutes to try it, and we'll look at the solution together. Okay, so it seems like people have started to finish and everyone's getting different answers, which is a sign that it's a useful question. Okay, so let's look at the solution together. So we want to know how many strings of length less than or equal to 5 are in the language. And we have this language that, uses regular expressions. Okay. So the first thing that, you can't always use this as a rule, but the first thing that I'm going to do, because I have a union here, I know that at some point when I'm going to count this, right? If you want to count the number of elements of length less than or equal to 5 in here and here, you're going to at some point need to look at the intersection, because what you could do is you could count the elements of length less than or equal to 5 in here, count the length of the elements of length less than or equal to 5 in here, and then subtract the intersection, because you don't want to double count, okay? And so what I want to look at first in this situation is I want to see what is actually the intersection. So what is the intersection of my language? Okay, because you're going to see that this is going to make my life a lot easier when I actually try to solve each parts of this question, okay? So what is the intersection? Well, what you could see actually is that all of this language, right, is actually contained within all of this language, right? So you can see that L of A, B star A is a subset of L, A, B star, A star, B star, A, right? So everything in here that's produced can also be produced in here. Why is that true? Because just say, okay, just say for the sake of argument, this is always lambda, and say this is always lambda, then, yeah, good. Then this, and this gives you the same language as just using this, right? So yes, very good. Someone's got it. Someone's got the idea. So what that means is I can essentially just forget about this second part here, because I know that all of the strings of length less than or equal to 5 that I'm going to find in here are also going to be in here. So to save myself the kind of rough time of finding both, finding the overlap, removing the overlap, which can be stressful, can be difficult if you're time constrained. Then if you notice this kind of situation, then you can say, okay, well, what I need to do now, the only thing I need to do now is I just need to look at the strings of length less than or equal to 5 in this guy here. Okay, as someone pointed out. Okay, so I hope that's clear for everyone, right? So I hope that everyone sees that all of this language is a subset of all of this language just by fixing these two symbols, right? Okay, so that's the first thing you need to notice before you start kind of brute forcing it, but not quite. So now that you've noticed that, and you move on to saying, okay, now I want to find the strings of length less than or equal to 5 in this first language, A star, B star, A. Then, yes, okay, so Kelly seems to have gotten the idea, very good. The idea here is, because I want to do this systematically, I know that I want strings of like less than or equal to 5. So what can actually happen here? How can I actually get strings of length less than or equal to 5? Well, the first string of length less than or equal to 5 I could get is if all of this just gives me lambda, right? So I could get strings of length 2, right? I can't get less than strings of length 2, of course, because these two symbols, these two symbols must be in the language denoted by this regular expression. So I know for strings of length 2, I'm going to have AA, right? So this is going to be a 1, okay? The next thing that can happen is I still need these two guys. I still need these two A's. But now what I can say is I can now get a string of length 1. I can add a string of length 1 in here, right? So what that's going to help me do is that's going to give me strings of length. So I have 2, and then I'm going to say, okay, now I'm going to look at the situations where this gives me a string of length 1. So in total, I'm going to get strings of length 3. So it's going to come from A, and then it's going to come from B star, A star, B star. So what are the strings of length 1 that I can get from this regular expression? Okay. Yes, very good. I can either get A, so I can either denote A by saying this is lambda, and I recognize an A, or I can get B by saying this is lambda, and this recognizes a B. Okay. So what that means is from strings of length 3, I can get 2. All right. Yeah. So it seems that someone got yeah. So that's the faster trick. But I wanted to display it sort of brute force-ish, just to make sure that everyone's on the same page. Okay. So what's the next step? So I've looked at strings of length 3. The natural next step is to look at strings of length 4. Right? And again, it's the same idea. I have to start with an A, I have to end with an A, and in between here, I want to look at the strings that have length exactly 2. So if my alphabet is AB, the number of strings of length exactly 2 are, as someone said, so if I have my alphabet is AB, the number of strings of length exactly 2 is going to be the cardinality of sigma square, which is going to be 2 square, which is going to be 4. And in fact, if you look here, I can get any of those 4 strings from this expression because I can get AA from this guy. I can get AB from this guy. I can get BA from this guy. And I can get BB from taking this guy, skipping this guy, and then taking this guy. Okay, so from this sort of idea, I get 4 more strings. Okay, and then the last version, or sort of the last length 5, is again the same idea. Here I have A, and then in the middle I have B star, A star, B star. And if we can, yeah, let's list all of them just for the sake of sort of completeness. If we list all of them sort of in a comprehensive way, BA and BB, right? So you can just, if you haven't learned this trick yet, this is just like incrementing binary strings by 1, which I'm assuming almost everyone here saw in 228. So it's kind of essentially the same thing. And so here I have 8 strings, and if you kind of just do a quick pass over all of them, you can see that this is recognized by the regular expression. So is this. This, however, is not. It's impossible to start with an A, right? Because to start with an A, you need to start here, and then continue with a B. So then go here, and then finish with an A, because there isn't an A star here, right? So this is impossible to capture, but this is fine because I can use this. Same idea for this. BAA, I can use B star, A star. BAB, clearly I can use BAB from the regular expression. Again, the same thing for BBA, and again, the same thing for BQ. Okay, so in other words, from here, what I get is I get 7 strings. Okay, so if you sum all of these up, if you have one string of length 2 plus 2 strings of length 3 plus 4 strings of length 4 plus 7 strings of length 5, then that's 14. Okay, and that gives you the number of strings of length less than or equal to 5 in this language. Okay, ABA is not accepted, so let's look more carefully at the regular expression. So we have B star, A star, B star, and we want to know if ABA can be denoted not generated, Ronaldo. So that's a very important distinction to make. Regular expressions do not do not generate languages. But okay, it seems that Amadeus got it. Okay, but yeah, so just because essentially you can't get that third A here, right? Basically, it's okay. You've been answering all of the questions correctly, so I'll forgive you. All right. So, are there any other questions about this problem? Okay. So what did I want to say just in general about this? Yeah, so in general, just before you try to answer questions like this, where you want, stuff of length less than or equal to 5, so it could have just as easily been, an FA or a grammar, make sure to see if there's a way to not completely brute force it. So in this case, I noticed something like this, and so that allowed me to prevent a total brute force and waste maybe 5 or 10 more minutes just on this question. Which is fine if you're practicing, but it's more stressful if you're in a test. Yeah, so that's essentially what I wanted to say about regular expressions, and also make sure you know sort of the classic kind of fallacies about regular expressions, like for instance, R plus S star is not equivalent to R star or S star. So that's a biggie. That's something that people often confuse because they think, oh, you can just distribute the star, but you can't do that because A or B star is certainly not the same as A star or B star. Okay, so things like that for regular expressions, which I'm sure you've already seen in the quizzes and also in the midterm, are important to kind of make sure you can recognize. Okay, and the same thing can be said for regular grammars. I didn't include an example just for the sake of brevity, but also make sure you can recognize edge cases for regular grammars and also making sure that you understand. So just let me, as a side note, for regular grammars, right? I'm sure this is a question that came up in the midterm and in the quizzes, but if G is a regular grammar, then L of G, the language generated by the grammar, is regular. Right, so you can have this direction. But if the language generated by a grammar is regular, then this does not necessarily imply that G is regular. So those are one of the kind of sillier and sort of trappier questions that you've got, and you can sort of just generalize that to the other topics that you've seen throughout the course.
Can I just
yes
about that?
Yeah, go ahead.
Is the lower statement true because G could generate the language in a non-linear fashion?
Yes. Well, so remember, what's the definition of a regular grammar?
It's
a grammar,
like right linear or left linear grammar, right?
Yeah, very good. So, but if I have something like S gives me AB, and then A gives me A, and B gives me B, then yeah, like you said, this isn't a linear derivation or a linear production rule. So that's why it causes it to be a non-regular grammar. But clearly you can see that, the language generated by this guy is AB, and it's finite, so it's clearly regular. So yeah, that's the distinction.
Right. Thank you.
No problem. Good question. All right, so that was for exercise 3. How many? Okay, all right. So so I didn't include as I said, a question for regular grammars, but I think that's kind of one of the most important points. Make sure you know, also for regular grammars, make sure you know how to do sort of derivations, be quite familiar with derivations, how you can derive different strings from a given grammar, and how you can sort of easily recognize patterns that are produced by regular grammars, but also, of course, on context-free grammars, which we'll look at in a few minutes. Well, yeah. All right. So is that all I wanted to say about? Yes, I think it is. Yeah. Okay. So the next question and the next topic is about the pumping lemma for regular. So I should specify it's for regular languages. So this is one of the classic questions where you're given a language and you're given a choice of strings that you could use to derive a contradiction, and you want to pick the one that could give you a contradiction. So that's kind of a classic way of testing students on the pumping lemma. So I'll give you a minute to do this one, and we'll look at it together. All right, so it looks like some of you start to answer, and you all have the same answer, which is good. Okay, so what is the question asking? So we're given this language here, which is the union of A star B star with A I B J C K for the number of A's has to be strictly less than the number of B's, and the number of B's has to be strictly greater than the number of C's. Okay, so we're given M to be the constant of the pumping lemma, and we have some choices for W. So is A going to work? So let's say I say W is AMB. So first of all, is this a valid W in the sense that it belongs to the language L? Yes, it is valid because you can sort of identify it from here. But remember what happens in the pumping lemma. You then try to identify a decomposition XYZ of your string where you're going to pump up or down the member of the string Y, right? So that's that small piece of the sequence Y, okay? And you can tell here that no matter what, no matter what way you pump up or down, right? So if you pump up, you would get something like A M plus KB. And if you would pump down, you would get something like A M minus KB, right? Because the Y has to be within the first M symbols. And in either of these cases, you don't get a contradiction, right? This kind of conclusion does not lead to, oh, well, this string is not an L, because it is an L because of this, right? Because of this guy is kind of making your life slightly more difficult. And so that's why you can't use this string to derive a contradiction, because in either way that you pump, so either if you pump up or down, you're never going to, so this is not going to be achieved. Okay, meaning that you don't come to a contradiction. Okay, so I hope that's clear. I hope it's clear why it's not A. And then, in fact, it's a similar reasoning for AM, B, M plus 1. So if you take, again, if you decompose this, you're going to have to decompose your XY, sort of Y being within the A's, and then your Z's can be anything else. So if you pump up or down, you're again not going to get a contradiction, because it's your pumped string is still going to be an L, because it's going to be able to be inside this first part of the language. Okay, so really what this leads you to conclude is you can't just have A's and B's. You need to utilize the fact that the second part of this language has a C. Okay, and so if you come to this option C, and you say W is AM, B2M, CM. Now, if you, so you know that you have to start pumping in here, so your Y is going to be in here, right? So now, if you can pump a sufficient amount of times, so if you can say, let's say you set your K to something very arbitrary, it could be, I don't know, M. So if you just set it to M, then you're going to get that your string is going to be, actually it might be M plus 1 to be safe. Or just to be safe, just set it to something huge. Let's just say 10M, right? So if you just set your K in your pumping length to something huge, then you know that your pumped string, the number of A's here is going to be a lot bigger than the number of B's here, and that's going to contradict this definition here. Okay, so that, yes.
In this case, if we put K equals M, wouldn't you get the same contradiction, because 2M is not strictly smaller than 2M?
Yeah, so yeah, let's try it, because I just wasn't sure, because it might be M, it might be M plus 1. So if you say Y is equal to, you know that Y is equal to A to the K for some K at most M and greater or equal to 1, right? So you have this, and you, yeah, so in the worst case, K could be 1, and you could, yeah, okay, so I think M would work. Because if you have, so W1 is A to the M, B to M, CM, then W2 is A to the M plus K, B to M, CM. So if you pump this, yeah, okay, you're right, yeah. So if you pump this M times, then you'll get A, M plus M. Yeah, very good. Yeah, good. Good observation. Because you'll get 2M is equal to 2M, but that contradicts this, that it has to be strictly less than J. Yeah. So very good observation. So that's also good. That's also a good practice question, or a good question that's possible to ask is, what possible pumping length could be used, and then you can see, oh well, that's not going to work because of something, and things like that. So that's another it's not in the set of questions, but that's another possible question that you could use at practice, and that I have no idea what's on the final, but it's a good question, right? Okay, so there's more questions in the chat, but let me just finish this last option. So this was for C, and then let me do D. So Okay, well, D is just not right because yeah, D is not right because if you take AM, BM minus 1, CM minus 2, then the number of B's is less than the number of A's. So this is already just not in your language L. And the first requirement for it is, the first requirement for a valid string in the pumping lemma is that your string actually has to belong to the language. If it doesn't, then, what's the point? So yeah, so that would be that would also be not good. So the only valid choice would be C. All right. Okay, so let me answer the questions. Is the whole final? Yeah, so it was mentioned in an announcement that it's MCQs and short answers. Yeah, so I'm not going to comment on the drive because that's dangerous for me. Okay, Vatica.
That's your drive, the one that this is on.
Oh, okay. I thought it was like a final exam drive. Okay, whew. All right. Okay.
I wouldn't dare do something like that here.
Oh, okay. Good. Okay. So yes, Ronaldo is you're being you're keeping morale up, which is nice. It's good. I feel like everyone needs this. Okay, so yeah, Vatica. Yes. So so Vatica, for C, we pump to M. Yes. So you can pump to M, right? Because then you would get right, because if you pump up by one, you get M plus K for whatever K is. But you want a contradiction. You want that the number of A's here is greater than or equal to the number of B's here, right? And so to do this, you at least need to pump by M, because then you're going to get 2M is equal to 2M, right? And then in that case, you already contradict this part of the this part of the definition of the language. Okay, I don't know if that answers your question, Radhika. Okay, D again. Okay.
Radhika here. I didn't know we could pump by M. Like I thought it was always pumping by I. So that's where I'm kind of confused.
Oh, I see. No, well, yeah. So the pumping is WI, right? But then you can just set your I to be M.
Okay.
Or you can also, like, you can set it to anything, really. You can set your I to M factorial, right? It doesn't really matter as long as it's an integer greater or equal to 0. Okay.
Okay, perfect. Thanks.
All right, no problem. Okay, Sharon, why does A and B not work again? So yeah, so people are explaining it, but let me just in general, why these two don't work is because if you take either of these two strings, right? If you take either of these two strings, then yes, it's true that they belong to L, right? They do belong to L. But if you pump up or down either of them, then you're going to be, so let me just zoom in. You're going to be pumping up or down here. So you're going to be adding K or removing K from either of them, okay? But that's not going to lead to a contradiction, because remember, the contradiction is you want WI is not in L, right? That's, you want your resulting pumped string not to be in L, okay? And that doesn't work here, because if you pump up or down, it's going to be recognized by this part of the language, okay? So that's why in general that doesn't work. All right. So I hope that's clear. I feel like someone unmuted themselves to ask a question. No? Okay. Alex, can you explain D again? Yeah, so D is quite easy to explain. You have AM, BM minus 1, CM minus 2. And already this choice of W is not valid because it doesn't belong to the language, right? Because if you look at this language definition here, what is it? So AM, BM minus 1, CM minus 2, that certainly is not in here, right? Because, you know, there isn't a C, okay? And that certainly isn't in here because the restriction is that the number of B's has to be strictly greater than the number of A's, okay? And that's not true here because M minus 1 is not strictly greater than M, right? I mean, if you take 5 minus 1, that's not strictly greater than 5, right? Okay, no problem. Right, so Jessica is answering your question, but the most optimum W would, yes. So yeah, so quote unquote, the most optimum, right? You can pick any, as long as your, what is it? As long as your string leads to a contradiction, I mean, it's just as good as any other string. But yeah, you could also pick AM, BM plus 1, CM. That would just make your life easier, right? Because then you would just need to pump up once. Like you would just need to pump up to W2, and that would give you a contradiction. So it's not that it's, you know, optimal. It's just easier, right? It's more straightforward. But this also works. Okay? All right, so I hope that's clear. If there are no other questions about this, we'll go to the next exercise. Okay, Nicolo, AM, BM plus 1, CM works. How come? Yeah, so it would work. So that's a good question. It would work if you were just looking at this language, okay? But you have that language union this language, all right? And so AM, BM plus 1, so no matter how, so if you have AM, BM plus 1, no matter how you pump up or down, yeah, okay, I think you got it, but no matter how you pump up or down, this is still going to be an L, and that's not going to lead to a contradiction. Yes, so that's a very good, that's a very good question. So the correct answer is C. But thank you, Simon, for that remark, because I agree it's not obvious. All right. Any other questions about this? So as you can see, I think everyone can tell why I expected this to take a long time. I think everyone's like, oh yeah. All right. No? Okay, seems good. All right. Okay, exercise 5. So it's kind of I mean, it's not strictly a closure property one, but it's kind of a closure property one. So I'll give you a minute to look at this, and then we'll look at it together. All right, so hopefully you had a couple of seconds to think about it. So let's look at what this question is saying. So you're given a language L, and you say that let L be some language over sigma. So what's very important here, and just in general mathematical notation, is when you say let L be some language over sigma, then you're not saying that it's all of the languages over sigma. You can pick, you're allowed to pick what L is, and then once you have that pick, then you can determine whether the following statement is true or not, right? So we have, if L star is finite, then all languages over sigma are regular. So, okay, so some people are saying true and other people are saying false. Okay, all right, okay, good. So the idea I wanted to actually, yeah, so I'll come back to it later, but the idea I wanted to come across in this question was never under any circumstances when you look at this question, forget about L is equal to sigma star, L is equal to the empty set, and L is equal to the language containing lambda. Okay, because in a lot, I mean, in not all of them, but in a lot of true-false questions with this kind of wording, these languages can like save your life. Basically, they can immediately help you out and let you figure out if something is true or false. And so if I'm saying that, then it might be a hint that this might not be true. And in fact, let's say you have L is the, let's pick the empty set, right? Then if I do L star, what is that going to be? So sigma star, what is that going to be? Well, let's just, again, don't forget your definitions. What's the definition for this? Sigma to the 0, union sigma to the 1, union sigma, whoops, union sigma square, union sigma cube, and so on, right? So for any of the languages here, you're just going to do, sorry, I was saying sigma, I meant the empty set, sorry about that, yeah. The empty set, you're going to take the empty set and concatenate it with another empty set, right? So you're going to do something else. But we know that the empty set concatenate anything else is going to give you the empty set, right? So you're left with the empty set to the 0 union the empty set, right? And the reason why I kept the empty set to the 0 here is because there's an important property for languages that says that L to the 0 is always the language containing lambda. This is true for every L, okay? So for all. What's very important to note is, it's very similar to, you have a mathematical expression, you raise that to 0, that's always 1. So it's the same kind of principle here. You have any language, you quote unquote raise that to 0, and you get the set containing lambda, okay? So that means that I have the set containing lambda, union the empty set, and that just gives me the set containing lambda, right? So L star is finite, right? It's for sure finite, it has one element. But if, for example, sigma was AB, then it's not true that all languages over sigma are regular, because, for instance, I could just take L is AN BN, and I can immediately say that this statement is not true, okay? And this also isn't true if, for instance, I replace this with all languages over sigma are context free, right? Because you could take AN, BN, CN. If you sort of add C to this, you could take AN, BN, CN, and just as easily show that that's false. All right, so yeah, so the main idea I wanted to come across here, that I wanted you to sort of see here, is never to forget about sigma, the empty set, and the set containing lambda. Yeah, that was the main idea for closure properties and things like that. Are we allowed to set the sigma the same way we set the Yeah, so in this case, sigma is also arbitrary. So it doesn't say over all sigmas. Yeah, so yeah, it doesn't change anything, but yes, you can, as Ronaldo was saying. Question? Yeah.
Yes, quick question.
Yeah.
So is the answer to this false?
Yes, 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 yes.
Okay, but didn't we just say like if L star is finite,
Yeah.
like what was the counterexample? I didn't understand.
Oh, okay. So okay, well, you get L star is this, right?
Yeah, this proves that
This
that statement. This
it-
is like
it-
an example, a working example.
Yeah, it's a counterexample where you picked an L, right? You picked L as the empty set.
Yeah.
So now L star is the set containing lambda, which is finite because it has, one element.
Right.
But now, so maybe the mistake that might be confusing you is I picked the same L. Let's just say, because the statement is then all languages over sigma are regular. So not just L, all
Oh,
languages.
okay.
Yeah. So
Oh man, yeah.
Yeah.
I see
so
now.
yeah, okay, good, very good. So yeah, so another point about these types of questions, like specifically closure properties, is be very careful about the wording. Make sure you read it a couple of times, because based on how it's worded, you can correctly conclude that the statement is something, but you just you didn't read the statement correctly, and so that messes things up. All right. Okay, so yeah, so Vatica, Y is phi, or the empty set. What do you mean? Oh, I guess phi star is lambda. Yeah, so maybe let me just go over that again. Phi star, right? Just if you apply the definition, you have this, right? And what I observed is essentially for each of these guys, what's happening is you have the empty set concatenated with L, right? Well, let me not use L. I feel like it's confusing everyone. The empty set concatenate with some other language is going to give you the empty set. So the empty set union itself a bunch of times is going to give you the empty set, right? So now you have the empty set to the 0 union the empty set, okay? If you have X and you do union the empty set, that's going to give you X, right? Because you're not adding anything to X.
But why are we concatenating though? Like,
Concatenating here?
yeah.
Well, that's just the definition, right? So phi square is just phi concat phi. And phi cube is phi concat phi concat phi. So if you have this language here, if you have the empty set, and you're concatenating it with anything else, then it's going to give you the empty set anyways. So the pause means you didn't get it, but
Yes, I got it actually.
you did? Okay, because usually pauses means, okay, very good. So all right, so that's why you're concatenating. Concatenating gives you the empty set. Now you have this union the empty set, so you have this union the empty set. And as I was saying, anything union the empty set gives you that anything, right? Then, so this is going to give you the empty set to the 0. And you have a property that's L to the 0 is equal to the set containing lambda. And this is true. This is true for every language L. Okay, so this is always true, right? And so because of that, you have the set containing lambda, right? So you have a finite number of elements. And so if I go, let me go to the cleaner. Let me just clean this version out. So L star is finite, right? L star is finite. I have an L here, so if I have L star is finite because I have a single element. But if you take any other, so if you can take another language, because remember what the statement is saying. It's saying then all the languages over sigma are regular. But that's simply not true. If you take a certain language, for example, ANBN, then that's not regular, and so this proves the second part of the statement. Okay. So let me check for questions. Okay, so hopefully Celia understood the counterexample now. And people are explaining, yeah, is lambda because, yes, very good. What if it says if L star is regular instead of, yeah, so if L star is regular, then you can actually use the same counterexample. But Stephen, I feel like someone miscorrected. Yeah, so definitely finite does not equal regular, right? Because then regular languages would be very boring if they were only finite. But all finite languages are regular. If it said if L star is finite, then L is regular, yeah, that would be true, 100%. Conversely, regular is not, yeah, good.
So why exactly this is false? Because of A and BN?
Yeah, because I can pick, because it says then all languages over sigma are regular. All languages, right?
Oh.
So every possible language over sigma is regular. So that's definitely not true because I can just pick one language here. That's not regular, right?
Yeah.
Okay, good. Okay. I'm starting to have trouble keeping up with the chat. Okay, yeah, no one's staying mad at Ronaldo. So finite equal regular. Okay. I don't. The equals is really messing with my mathematical. Okay. If L is finite, then it implies that L is regular. If L is regular, it most certainly does not imply that L is finite. All right, so that's and remember what the reason behind this is. If L is finite, then you can just, in a regular expression, you could just say the regular expression is the first string S1 or the second string S2 or the third string S3 and so on. And you can do that a finite number of times, right? And then L of R would denote the language L. And so that would prove that L is regular, okay? Because AN is, yeah, very good. Thank you, Ronaldo 3. Programming wise, okay, all right, so that's, okay. All right, so none of the questions at the end are 335. Okay, is this, I feel like this is clear. If people are starting to joke around, then it's fine.
I just want to make sure one thing. So ignoring the A and B N, what does L star with the empty set prove?
What does L star empty set?
Does that prove anything? The L star equals empty set?
No, the point of the L star where sigma is the empty set just shows that it's an example where the L star is finite. But this doesn't apply. Just because that's true doesn't mean that for all languages over sigma.
Yeah, so it's really only the A and B N that we need to actually to use to prove there's a contradiction?
Yeah, the ANBN is used to show that there's a contradiction. Yes.
Okay.
Yeah. So I mean, yeah. So I feel like the question is, what's the point of the question? And yeah, it was just to make sure that everyone is familiar with using sigma star, the empty set, and lambda to use in counterexamples. But then, yeah, at some point, if you want to show that the language is not regular, then of course, at a certain point, you're going to have to pick a language that's not regular, and one of the famous ones is ANBN. Yeah. Nicolo, but you still need to, yes. So yeah, so the point of picking this, is because it gives you L star is finite. So because it gives you that the first part of the statement is true. So the first part of the statement is true, but then you can show that the second part of the statement is not true. And so if that's the case, then it's false. Okay, so remember to 232, T implies false. So this, right, this statement is false, right? So I know it's confusing because I'm saying false twice, but just remember from your 232, I know that might be way back for some of you, but true implies false is always false. Okay, so that's why I'm using that. Yeah, so that's why the L star is there. L star of lambda is still lambda, right? Yes. So the other question, the question is, if L is lambda, then L star is, yes, it's most certainly this. Yeah, so this is true. And you can just work that out easily with kind of expanding the definition. Okay, any more questions about this? What time is it? Okay. All right. No, it doesn't look like it. Okay. So yeah, so the main idea, again, the main takeaway from here was that I wanted you to make sure that you remember that you can use sigma star, the empty set, and lambda for counterexamples. And I encourage you, while you're studying, to just try to make these up as you go, kind of, because it's super easy to try to think of some questions. They might not be useful, but they might be good for studying. You know, you just create a statement and you try to sort of easily show that it's not true using this. So that's good practice for studying. And maybe, yeah, so that was for, yeah, so I feel like that's everything before the midterm. For the, yeah, and then just for the pumping lemma, I didn't say it before, but for the pumping lemma, you know, make sure that you know the statement, like, you know, by heart, basically. You need to know what the pumping lemma says. And you need to know how do you use it to show that that a language is not regular, the different ways of picking strings, and so on. Okay, so my voice is dying. So what I think we should do is so I can answer questions, but maybe for those of you who want to do the exercises, you could try to do the exercises for the next section, and I'll just answer some questions. Yeah, so that's what I wanted. I wanted to take a break. So if there are no questions, we can take like a 10-minute break or something, because that might be helpful for everyone. Yes. So I think 10 minutes is good. Yeah. So let's meet back. Well, I'm not going to close the session, but let's meet back at 4:12. All right. And yeah, so this is very sad. I wanted to do a second review tomorrow, but I've been told not to. So yeah. So there won't be. So this will be the final review. the final review in the sense of final exam, and also and also final, like, you know, no final. Like it won't be, anyways, everyone sees what I'm saying. Yeah, I'm sorry. Yeah, I don't, yeah, I'm sorry. I don't have much of a choice, I'm sorry. We'll see. Well, no, but I mean, it's definitely recorded, right? So this is recorded. Yeah, so that Ronaldo could definitely do that. Yeah, I agree. So, but yeah, so let me actually, I'll stop recording so then the file doesn't become too big.